So overallly, the new pickup current value as well as the new time dial setting values are calculated based on the change in system configuration in order to protect the microgrid. Also, one of the proposed method consisting of superimposed adaptive sequence current. In this method, what we did initially, the simple network is represented in a symmetrical component diagram. Generally, the analysis as of now is conducted by showing the source as well as loads for a balanced system. This network shows a unbalanced loads also considered. So initially, the circuit shows when switch S1, F1 and switch S1, F2 are open. This network diagram shows for a simple unbalanced network symmetrical component representation. Whereas when a fault F1 occurs in a system or F2 occurs, there is a change in network configuration. Based on that, currents were calculated. So in a overall, the adaptive fault current is also calculated using the formula, which is ratio between the positive change in superimposed positive sequence current upon uh, superimposed positive sequence fault current and pre-fault current. Actually, the main purpose of determining the adaptive fault current, which is based on the positive sequence current and negative sequence current, and a impact factor is during the fault conditions in a islanded mode, the fault current contributed by the DGs is not more than 2 per unit. Therefore, the impact factor is calculated based on the mode of operation and the presence of GG, presence of distributed generation. A particular impact factor is calculated in order to bring back the fault current into within limits. The proposed analysis have been verified using a hardware relays in a hardware in loop diagram. So that the system studied consisting of a real-time digital simulator where the power system can be modeled using various generation, transmission lines and distribution network loads were modeled in a power simulator, and GTII, Giga Transceiver Analog Input card allows in order to input the circuit breaker status, whereas GTAO, Giga Transceiver Analog Output card gives where I can extract the three-phase current and fed back to the microprocessor or D-space processor where the proposed algorithm is implemented in D-space processor and the proposed algorithms were verified. The simple results were shown here. A portion of network is considered where a nodes 834 and 860 and 836 where lines were connected. R5, R6, R7, R8 shows a relays locations and several fault location F5 to F8 are shown in this diagram. For example, when a fault occurs at point F6, as I said, relay R6 acts as a primary relay, and under null operation, in order to backup, relay R8 act as a backup relay. So under fault F6 condition, the conventional relay, simple directional overcurrent relay, is unable to provide the protection for a network as shown in the diagram A and B. Whereas using the proposed relay algorithm, adaptive superimposed sequence current relay, the R6 is able to determine the fault within limits initially, whereas the R8 is providing a backup as shown in this diagram, and it is able to satisfy the constraints like the protection is able to operate within 0.1 second, as well as it is able to maintain the protection coordination between relay size 0.3 seconds. So microgrid consisting of various distributed generations as well as network and loads are having various issues related to the islanding detection and traditional relay schemes. Based on the measurement of voltage and current values at the relay location, islanding detection and protection schemes are proposed for a grid connected and islanded mode of operation, The proposed method are able to determine the islanding and non-islanding events within limits. Non-detective zone is also one of the issue for a passive type of islanding detection method, which can be overcome by using the proposed method. Due to change in network mode of operation, the direction of pre-fault and fault current, also level and pre-fault and fault current is varied. The adaptive relay techniques are able to provide the protection for microgrid network. Let me take into the other one of the topic which I'm working on, actual data considered in a southern region. So the power grid in India is southern region is one of the portion of national grid of India. The actual generation as well as the transmission and distribution network existed in southern region is considered and proposed a transition plan for the future scenarios for year of 2023, also for the year of 2027. How will be the transition going to be take place in southern region grid is studied. So there will be various issues due to slow growth of projected demand and less efficient performance of thermal power plant, also renewable energy, fast growth of renewable energy sources. So out of which we been taken portion of thermal power plant in order to improve system performance. What we proposed is, as a part of energy policy, our team at NIAS has proposed that the old thermal power plant are having uh, issues related to the water consumption, environmental issues, system plant load factor or efficiency, as well as in order to improve them, it is considered that old thermal power plant, old here means which are older than 25 years and capacity of 500 megawatts are considered in order to save the retrofit cost also, because in order to improve their performance, a investment may be required. Therefore, what we propose, retire them the thermal power plant. Also, there will be renewable energy sources, also thermal power plants which are under commission may be considered in order to improve the or to meet the projected peak demand. So the my part of study consists how can we meet the peak demand for the year of 2023 and whether the system is able to operate in a limits like a voltage limits, also able to meet the projected peak demand. If not, what will be the amendments or grid modifications are required or proposed. Similar analysis also studied for year of 2027 scenario. As I mentioned, the electrical power survey has proposed or have given a projection, load projection for the year up to year 2027. Based on this projection, the in capacity of generation is planned in southern region. It can be seen that the wide gap between the projected and actual is been increasing from the constantly from the last 4 years. Even the projection values as per the 19th EPS, 19th Electrical Power Survey also shows that there is a wider gap between the projected demand as well as the actual demand. This gives an opportunity to improve the system performance by retiring the old thermal power plants. This diagram shows the various thermal power plant proposed for retirement in southern region. Southern region consists of 5 states: Tamil Nadu, Telangana, Karnataka, Kerala, and Andhra Pradesh. It is found that around 8 gigawatt or 7,900 megawatt, which are 47 thermal power plants or units, were likely to be retired with the proposed method. Whereas similarly, around a 6.3 gigawatt of thermal power plant which are under construction are likely to be commissioned by 2023. Also, there is, in order to import the power from other region, the southern region is also integrated with western and eastern regions. There were two inter-regional transmission lines from Varogara to Warangal as well as Raigal to Pugalur, which are under construction, can be expected to be connected by 2023. With this addition, the total projected inter-regional transmission capacity is going to be likely 30 gigawatt. So what I did in this analysis, we been considered the projected peak demand in every state, and studies power flow analysis studies using conventional Newton-Raphson power flow has been studied using PSSC simulation tool. We've been modeled with the help of Southern Region Load Dispatch Center in Bangalore. We were able to model the network for a 2023 detailed network, which consisting of extra high voltage to low voltage network, and we were able to conduct the studies where how the peak demand is met as of now 2019 we initially studied, and similar projection we made for the year of 2023. What we observed is almost 80%, that is around 18 gigawatt of thermal power is helping to meet the peak demand. Similarly, the southern region is also blessed with various types of energy sources like gas, tidal, wind, nuclear, and the contribution by each state is shown in this tabular form. As I said, and the generation is also can be segregated into two parts. One is state entity, the generation which is made within state, and the generation which is comes to the category of regional, but which is presented in southern region itself. Other is third portion is the power generated from other regions, where I can name as outside SR, which means either western region or eastern region. So from this analysis, we found that around 22 gigawatt of power is likely to be required in order to meet the peak demand. So a clear distribution how we can achieve the 22 gigawatt of peak demand, import from western to southern region and eastern to southern region. The presented line are shown here. So overall, the study is conducted in order to determine loading capacity of substations as well as transmission lines, whether the system is able to operate within limits or not. We found that in order to compare to the 2018-19 scenario, the system is able to improve the performance with the proposed analysis. Also, there will be several substations were found to be operated under its maximum capacity or may not able to feed the power under absence of particular backup component or element, which I can say as under contingency n-1 contingency scenario, it may able to provide some issues. Those we proposed a certain capacity under substations in order to validate the proposed studies. Overall, the proposed method is provided in a form of economics. Also, environmental issues can be overcome. One of the requirement in order to increase the generation from renewable energy sources is to improve the flexible operation of thermal power plant. Here, flexible operation of thermal power plant means generate the power under reduce the power produced by thermal power plant when renewable energy sources are providing maximum power. For example, under daytime, availability of solar power is there in order to feed the load. We can able to reduce the flexibly, we can able to reduce the power generated from thermal power plant. Therefore, maximum power can be extracted from renewable energy sources. Similarly, under the absence of renewable energy sources during the night times, for example, solar power, vice versa, increase the power generation for thermal power plants. Also, the similar analysis is extended for the other regions, western region, eastern region, and northern regions. One of the observations which I made during these studies is, though apart from the power flow studies, there will be various issues like control issues, protection issues, also reconfiguration of network, are are doing manually as of now. There will be a limited automation, and uh, even operation of circuit breakers, though the SCADA is implemented in few of substations as per my knowledge. With the implementation of communicated assisted devices like distributed energy resources, phasor measurement units, IEDs for protection analysis, we can able to improve the performance of actual power grid scenario. Okay, coming to the power sharing among hybrid AC DC microgrid is studied in this topic. Okay, do I have time, right? Can I take more 10 minutes, please?
Sure, sure, Dr. Harikrishna.
Okay, thank you. Okay, so as I said, ACS means AC subgrid. AC subgrid is collection of various distributed generation which is connected to transmission line and loads. Similarly, DC subgrid, which means having only DC sources and loads and DC loads. I in order to operate or analyze the multiple AC subgrids, all AC sources within a some location is named as ACS1, AC subgrid 1, AC subgrid 2, and DC subgrid 1. In order to feed the load, there will be a generation and load unbalance between the AC subgrid 1 and AC subgrid 2. Similarly, DC subgrid 1. I made an analysis of how many scenarios it can able to generate. One of the, it can provide the 3 scenarios in a presence of 2 AC subgrid and 1 DC subgrid. Sorry, the purpose of interlinking converter in our is helps us to provide power from AC subgrid to DC subgrid, similarly DC subgrid to AC subgrid. For some time being, I'm not discussing about much about control and protection issues. The scenario shows that when a AC subgrid 2 is overloaded and AC subgrid 1 is underloaded, means more generation, the power can be transferred from AC subgrid 1 to AC subgrid 2 using interlinking converter 1, DC subgrid 1, and interlinking converter 2. Similarly, other scenario is, I can define as DC subgrid 1 is having more generation in order to feed the AC subgrid 1 and AC subgrid 2. And the third scenario is that AC subgrid 1 and 2 are having more generation which can able to feed the power from DC subgrid 1. In this way, the power can be transferred from one generation to other generation. This will help us to reduce the curtailment of renewable energy sources as well as thermal power plants. Similarly, the analysis can be further implemented to when DC subgrid 1 and DC subgrid 2 are there, which are connected to a single AC subgrid 1 using interlinking converter, where interlinking converter provides the bidirectional power between one subgrid to other subgrid. So overall, it can be concluded that in a multiple AC microgrids, following scenarios may occur. Even I take a 10 multiple microgrids or 100 multiple microgrids, maximum scenarios can be desegregated as 3 types, either power flow from AC to DC, and or AC to DC and DC to AC. Last one is DC to AC and AC to DC. So the power sharing methods can be studied or in a literature review consisting of either it is communication assisted method, decentralized method, or measurement of local parameters is used. One of the method is group control method for a power sharing in AC DC microgrids. It is similar to the conventional AC power sharing method, where having the relation between the active power and frequency provides us in order to share the power among the DGs. Similarly, the reactive power also can be shared using the constant, that is AC droop gain constant, and NAC indicates the reactive power droop gain constant. So the droop gain constant can be computed using the difference between the limits of angular frequency upon maximum capacity of DG. Where in a AC subgrid, we know the parameter which is global is frequency, whereas DC subgrid are having direct current is having zero frequency. The other we can take a parameter as a global is voltage. So based on the DC voltage, the droop characteristics can be similarly we can implement for DC subgrid also. So in these droop control, using these droop control characteristics, power sharing among the DGs is proposed and find analysis. For a simple AC microgrid, I have shown a characteristics between power and angular frequency. The MAC indicates the droop gain of AC subgrid. I can define it as, even though AC microgrid is having more number of DGs, it can be cumulatively computed, aggregated as a one droop gain, which gives the same analysis as MAC1 and the nearby other microgrids where I can name as MAC2. When, for example, a maximum load is applied, as shown, we can see from the characteristics that those are having a negative slope. Under minimum angular frequency, the maximum power is generated from each DG, which indicates the PAC load, means maximum load in AC subgrid which can able to sustain. For example, I increase the load by more 2 times. Therefore, the same load is shared between the two microgrids or subgrids, but they do not have power to feed those loads. Therefore, those condition can be considered as overloaded scenario. So this overloaded power can be received using a interlinking converter. That is, either it may be provided nearby DC subgrid or other AC subgrid. In this way, the power sharing can be achieved in a AC-DC microgrids. However, okay, a simple study analysis is shown in this diagram when AC microgrid is consisting of two DGs, similarly DC microgrids along with the DC loads, and the power is sharing between AC to DC or DC to AC. The controller in invert control circuit has been modeled for interlinking converter. Also, the system is considered based on the conventional network. What I observed is when the power is flowing from DC to AC subgrid, for example, I can able to see the stable characteristics. However, there will be small oscillations in the system has been observed when the power is flowing from AC subgrid to DC subgrid. Also the reason behind the significant reason behind the oscillations has been studied using the eigenvalue analysis. So what are the factors really affecting the system has been studied. It is found that the dynamics of AC subgrid, where the factors like angular frequency, also the droop gain values MAC are affecting the system, which are making a oscillations in the network is observed. So one of the method we proposed in order to reduce the oscillation is uh, by increasing the generation in DC side, we can able to reduce the small signal analysis, or this type of oscillation issue can be overcome by increasing the DC generation capacity. So the impact of bidirectional power flow on the stability has been studied. Also, when the more number of interlinking converters are presented in the network, the issue of power sharing also may rises. It required communication assisted device in order to improve the power sharing among DG sources. So as of now is simple two scenarios like power flow from AC to DC subgrid and power flow from DC to AC subgrid is studied in order to determine the dynamics. and what will be the recommendations required. Okay. Okay, my future work consisting of multiple microgrid means it is a cluster of various grids or sources which are connected to distribution system or loads which can operate it in grid connected mode, islanded mode, as well as independently in order to feed the load. Also, the bulk grid power generated from bulk generation from grid is also need to be taken care. Cyber physical system, in my opinion, means it is having a layers as cyber layer as well as physical system, in my opinion, consisting of generation, transmission, load, where it is need to be controlled, protected using either switches, relays, monitoring devices. These protection control monitoring devices are having a communicated assisted facility in order to transform the information among them. So by using this communication assisted technology, the protection and controller algorithm performance can be improved in a fast under various scenarios. So one of the idea I proposed is to how in future it can be further extended. How will be the cyber physical system can be modeled in a simulator or using any programming or using hardware, and the evaluation of control and protection algorithm for in order to improve the network performance. Also development of new method for power sharing in hybrid multiple subgrid, and evaluation of these issues under various network configuration, either what is the effect of type of DG or place of distributed generation may also affect, which is already defined in a literature review, and it need to be validated for various scenarios is required. Further, after that I'm interested to present those results in future in various scenarios. Thank you very much. If any queries and suggestions, I'm welcome, sir, all of you.
Thank you, Dr. Harikrishna. Do we have any questions? Hello.
Yes, sir.
Joy here. So just one question, if I may. Actually, I just needed a little bit of information on AC and DC microgrids. If there is a question of power flow from one to the other, how does that happen? Because one is DC. So do you have specific devices in the middle which do this, which make this possible?
Sorry, Joy. Actually, your voice got interrupted. Can you please repeat your question?
Yeah. So I was asking that there are several AC and DC microgrids, and there is a question of transferring power from one to the other. Now, so does this require special devices in between? Because automatically they cannot be synchronized together, I think. So what is the way of doing this, transferring power from AC and to DC microgrids and the other way?
Yes. Actually, if I see, it's a very nice question. In a power sharing in a AC microgrids, as I said, it is having a common parameter known as frequency. Whereas in DC microgrid, common parameter we are having DC voltage. So in order to transfer power through interlinking converter, there is those two parameters are having different domains. So it is necessary in order to bring them to a average value. Therefore, that will provide a facility in order to determine how much power need to be transferred from the one device to one grid to other grid. Like we can normalize the frequency and voltage into certain level in order to transfer the power. However, further when we extend in a multiple interlinking network, it may not able to provide the actual power references required in order to transfer the power. Yes. So therefore, it required either we can need to monitor using any communication assisted relays or protect control devices in order to determine or how much power need to be transferred within a particular time. Yes.
Yeah, but I was trying to understand, do you need something like frequency to voltage and voltage to frequency converters, which will basically bridge the two types of network?
Yes, it required a frequency measurement as well as voltage measurement on the both sides of interlinking converter.
Uh-huh.
Yes.
Okay.
Yes.
Okay. Fine. Thank you.
Thank you.
Dr. Harikrishna had what I read was that one reason for lack of acceptance of DC microgrids is the safety aspect, that somehow the equipment has to be derated by a factor of 2, that voltage, like half the voltage, for maintaining the safety clearances and all. So is this a big issue? And then is it like if you have DC microgrid, is it the major problem for having the microgrids with DC instead of AC? The safety aspect of DC.
Safety aspects varies based on the standards as well as countries. I am not sure whether you are speaking about the voltage limits. If it is a voltage limit, yes, the DC microgrid is also need to be maintained or designed within a standards. But I'm not sure exactly. I need to look into that. What are the standards for DC microgrids?
Okay. And in your analysis, have you looked at the conversion efficiencies? So as I believe that DC to AC conversion efficiency is much lower than AC to DC. Is that correct?
Okay, actually, in my study, I've been taken as an average modeling of a complete network. A conversion efficiency I maintained into the same value way because I normalized the system or averaged the system. Therefore, I think the conversion efficiency will be very well known when we model a detailed interlinking converter or in a system.
Okay. So what is the current state of the art about efficiencies that you can get in the reasonably, like regularly used systems that you're considering?
Oh, sorry, I don't know efficiency. Yes.
Okay. Thank you.
This is Nitin here. I have a question. So you mentioned about policy studies and this transition suggestions, recommendations that you gave regarding decommissioning of thermal power plants. So how do you model this? Is there a model based on which you come up with these recommendations?
Yes. Actually, the total Southern region grid is modeled in PSSC simulation tool with the help of Southern region load dispatch center, where we received the data of all thermal power plants as well as all generation sources, substations, and transmission line data we've been received by my team in the NIAS, where we've been modeled the data in PSSC simulation tool.
Okay, okay. That's so you get the data and you have a simulation tool.
Yes.
On what basis do you say that we need to discontinue thermal power plants and
Okay.
how many, in the sense, what capacity of thermal power plants
Yes.
should we decommission? And if we decommission, there should be an alternate source, right? So that also should be brought into the model. So
Yes.
I just wanted to understand how all these different parameters.
Actually, it is having two steps. One is transition of thermal power plants only based on the system performance from last few years is been tabulated, which means it is observed that the technology of thermal power plant which is inbuilt is is able to provide a more emission. The older thermal power plants are able to generate more emissions because of legacy in technology, whereas new thermal power plant are having more efficient, also less emission type of technologies were there. Based on these factors, we segregated the proposed retirements as well as the new additions. Further, in the next step, if these retirements and additions were taken in place in a network, how will be the effect the grid operation scenario is studied. So if we retire and addition is taken, how will be the scenario is affected is studied for the year of 2023 and 2027. Though the software is only in order to validate, we were not taken any factors from the software to propose.
Okay. Also, I'm new to this area, so one question: what would be an example of a DC sub microgrid or a DC grid? Are there DC grids in India?
Actually, DC grids on a pilot project these were existed in India under very small scale, under in the range of megawatt as a pilot project. We can say a satellite communication system like CubeSat, which mainly operate under the DC microgrid itself. I can define a CubeSat which as a DC microgrid which consume a power in the range of megawatts or less than megawatt. Yes.
Okay, sorry, I didn't get. CubeSat is a what is
so CubeSat required a power in order to feed the load in a satellite system. It is having a network configuration of DC loads as well as DC network, and the power is fed either using a battery or a photovoltaic system which is arranged to the satellite cube satellite, are in the range of kilowatts to megawatt. Those systems I can define as a DC microgrid because those are independent of a main microgrid which are able to feed the power to the load using a DC sources. Yes.
Okay. Any other questions? Okay, if we don't have any more questions, let's thank the speaker. Let's give him a round of applause.
Thank you very much.
Thank you again, Dr. Thank you
Thank
again,
you so
Dr.
much.
Harikrishna. We will stop the meeting now. Thank you.
Yeah, thank you so
Thanks.
much.
Bye.
Bye.